you have the stomach still for something completely different. We're going to talk about quantum mechanics, and how we can use quantum mechanics to make a new information-based system. Now, I'm a professor in physics, but I have a background in engineering, and I've put up two pictures to show you that we really make things. We're not only thinking about things, but also making things. And on the left, you see a picture in a clean room where we make computer chips, but quantum computer chips. And in the middle, I'm putting one of those chips in a system for measuring. Now, that system looks pretty old by now. It was, the picture is 10 years old. Nowadays, you see how it looks like in the right picture, and it's impressive also to people like Joe Biden. Although, you cannot see from his face that he's actually impressed, right? He has a blank face. I don't know if he's impressed, if he's thinking about something completely different, or maybe procurement or whatever, just blank. But I hope what he's thinking about is no, this is really a revolution. Because if we think back, if we look back at history, how information has been processed, then from very early days on, we've been using bits of 0 and 1s. That could either be an abacus where we put something up or down, or a mechanical computer as was used by Alan Turing in the 50s of the last century, or even in most modern chips that are used for AI. These are all based on encoding information in 0s and 1s. But what we found out about 2 decades ago is that 0 and 1s are not the most fundamental level of encoding information. There's a deeper level that is richer and also much more efficient in using for calculating certain hard problems. And that is quantum. And quantum was thought of about a century ago by people like Bohr and Einstein. And they thought about quantum in the context of nature. How does color arise? Why does certain atoms, illuminate certain colors? There's so many problems that have been thought of or could be explained with quantum mechanics. And there's a little formula up there, and the formula is hiding a lot of details, but it's a beautiful, simple formula that describes the basics of quantum mechanics. So that was quantum 1.0, and quantum 2.0 is how we can make technology out of those concepts of quantum mechanics. And probably the most central concept in quantum mechanics is superposition. That something can be at different locations at the same time. Now, in the time of Einstein and Bohr, they were thinking about atoms or molecules. And for instance, a hydrogen molecule or an oxygen molecule that consists out of 2 oxygen atoms. And how these 2 atoms are kept together is because of superposition. And to illustrate that, I'm adding an electron to the 2 atoms. So atoms have electrons, and I'm adding 1 electron to these 2 oxygen atoms. And the electron has to decide, am I going to sit in the middle? Am I going to sit on 1 oxygen atom, or maybe on the other? But what it actually does is it sits on both atoms at the same time. And please take this literally. It's not jumping back and forth very quickly that we cannot see where it is. No, it literally sits on both atoms at the same time. And this superposition is keeping the molecules together. And maybe you remember from your chemistry class covalent bonding. This is a covalent bond. If we would not have superposition, the molecules in your body would all fall apart and just fall on the floor, and we would sort of dissolve in atoms. Now, that concept of superposition we've been reproducing in artificial structures, in chips. So we went to this clean room and we made little boxes, little boxes in silicon. And the boxes are so small that it can hold just 1 electron. And if you put 2 boxes next to each other, we can encode a bit, let's say 0, if the electron is in the left box, or encode the bit 1 if the electron is in the right box. And that's one way of putting those bits into material, because you have to, at some point, you have to put it in a material. Now, this is all classical bits: electron in left box, bit 0; electron in right box, bit 1. Now, what the key and amazing thing is that people like me, but also people at other universities and in companies, have been able in the past 2 decades to put electrons in a superposition in different boxes. So we're no longer speaking about atoms that are really tiny, you cannot even see them. These boxes are visible by eye. And nevertheless, a single electron can be either in one position or another position at the same time. It's in a superposition. Is that useful for computing? And I made a little illustration of a labyrinth. And what a labyrinth problem is that you start somewhere in the middle and you have to find the exit. And what a computer does to solve this problem is basically what we do. You just try, and if you end up at a dead end, then you try again another path, and you do it again and again, over and over. But the good thing about a labyrinth problem is that if you find the solution, you know that you have the right solution. Now, quantum mechanically, with superposition, what happens is that all possibilities are tried out simultaneously in parallel. And also in this case, the quantum computer knows exactly, hey, I found the right answer. All the other answers I throw away, they were wrong, but the right answers I got very quickly because I could take all these paths through the labyrinth at the same time. So it's a massive parallel computer that is allowed by these superposition principles of quantum mechanics. Now, how does that translate to a computational problem? Chemistry is particularly difficult to calculate. To predict the properties of medicine, or materials, or anything that consists out of material is really difficult. That actually is so difficult because it's also a quantum mechanical problem. And to illustrate that, I plotted schematically the calculation time as a number of the atoms in the molecule. And for small atoms, our classical computers can actually solve the problem. But if I make the molecule bigger, then at some point, it takes a very long time. And we call that a hard problem. Now, when do we call something a hard problem? Well, for instance, when it's taking more time than the lifetime of the universe to calculate. And so it's not a low boundary, it's really, more, longer than that, it's really impossible. That's a hard problem. Now, I can do this calculation on my laptop, more or less the curve that I show you. I can use a supercomputer somewhere in the cloud that shifts the curve, but since it is based on the same principles of classical bits 0 and 1, it still is not able to calculate the chemistry of larger molecules. It takes the lifetime of the universe. Now, by using this massive parallel computing because of superposition, the prediction is different. Even larger molecules consisting out of more atoms can still be calculated because the way it scales as a function of that number of atoms is not exponential, but it's much slower. Let's say linear on this plot. So is this really a practical problem? Well, until 1 year ago, or 2 years ago, the fastest computer was actually built in China. You see all these racks, they're full of chips, they're full of servers. And what they could do is calculate the chemistry of a very important molecule, caffeine. But if I scale it a little bit, I add a few atoms to the system, because of this exponential complexity, already penicillin, also a very important molecule, could not be calculated. Already too difficult, already approaching timescales way beyond what is practical. And this is exactly the reason why people are motivated to build a quantum computer, because also penicillin or whatever larger molecule will still be able to calculate. Now, is quantum mechanics something very artificial, constructed by humans, unnatural? No, it's not. It is actually the language that nature itself speaks. If we zoom in on a leaf and look at how sunlight actually is converted into oxygen, we zoom in, then we see that the sunlight actually excites an electron in a very complex molecule. It finds its way by doing a quantum superposition over all the paths possible to the output of that molecule, and then it sends out the oxygen. So also that process of photosynthesis is run by nature via a quantum superposition. So nature computes using the language of quantum. Now, if you look at the applications that people think of to develop if we have this quantum computer ready. And I have a few applications that were put forward by the bigger companies that have been developing quantum computing. And these companies come from pharmaceutical companies, the big companies like IBM, Microsoft, all the big techs. And the applications that you see here range from electrical cables, a material science problem, where dissipation is completely absent. So you can send electricity from the desert up to here and without any loss of energy. Chemistry for medicine, machine learning, robotics, optimization problems, like logistics problems, traveling salesmen's problems, etc. Maybe procurement problems or also optimization problems. Handling big data for sequencing genomes or airplane design. So these are examples that were put forward by the different companies, including Lockheed for the upper left example. And I'm not sure if all of them are really suited for quantum computers. Actually, some of them can actually be solved by a classical computer. A quantum computer cannot solve everything better than a classical computer, but some problems it can, in particular the material science problems. Now, 20 years ago when we started to do this research, there were just university groups working on it, just developing small-scale devices and trying to discover the principles of quantum mechanics in these little chips. Nowadays, all the big companies, definitely in big tech all around the world, have invested heavily in quantum computing in particular. And please think about billions per company per year. So that totals up to a large amount. This is a list of mostly American companies, some Chinese companies, but also here in Europe, because of a large European fund, a 1 billion fund, there are quite a few startup companies in Europe and also, in particular, also in the Netherlands. So let me come to the question, can we make quantum technology actually work? To what extent are we making something that will be available for companies or for the public to be used and solve those problems? Well, you can read in press releases that the quantum computer exists. You can log in to an IBM website and use the quantum computer that they make available for the public, which consists out of something like 100 qubits. Now this is fantastic. This is hard work. It's amazing what we could not have predicted about 10 years ago, that we would already have a 100-qubit quantum computer. But if you think about what is really needed to solve these big chemistry problems, or applications like also breaking code, well, then it's a bit more challenging. If you put all the needs together, like input, output, calculation time, etc., then we need about 1 million of those qubits before we can actually beat the classical computers. And it's not because quantum is not so great, it's actually because the classical computers based on silicon have developed so fast. And actually to get the crossover point to make quantum computers faster than classical, about 1 million qubits are needed. So the 100 qubits nowadays available by different companies. I just took the IBM example, but there are also other companies. It should be looked at as a prototype. Now, where will it go? Well, probably like everything in big tech that is hyped a little bit. There are these expectations, rising expectations, but there will be a point where we enter a dissolution. The trough of dissolution as predicted for many of the developing technologies. AI has gone through such winters about 3 times. So it doesn't have to be just a single time. It can also be multiple times. Now the difficulty, of course, is to predict exactly where we are. Well, we're somewhere definitely on the riser, but when will there be the tipping point of dissolution? When will the venture capitalists who have invested so much money already in those technologies say, hey, where is my return? I stop funding you. and that will be the start of the turnover. We're pretty sure that we have to go through a winter to sort of clean up the hype around quantum computing that is around nowadays. But can we make quantum technology work? I say yes. There will be a time after the winter where the machines will work and will be available for solving all those problems. And with that message, I'd like to thank you for your attention. Thank you.